in Carson City, a 4.2 magnitude earthquake rattled beneath Lake Tahoe.
Some shaking up there in Tahoe today, rattled by a quake this morning.
Under the shimmering blue surface of Lake Tahoe, one of North America's most iconic alpine lakes, something unusual has caught the attention of scientists. What began as a routine geological survey has spiraled into a situation that experts are describing with urgent seriousness. Cracks have been detected beneath the lakebed, deep fissures running along the subsurface, stretching across areas where the sediment and bedrock have been undisturbed for millennia. The discovery has prompted geologists to escalate their monitoring efforts and, most notably, to issue a rare and ominous red alert. Before we start, smash the like and subscribe buttons for more updates. Lake Tahoe, straddling the California-Nevada border, is often celebrated for its clarity, depth, and breathtaking mountain backdrop. It's a destination that attracts millions of visitors every year for recreation and natural beauty, but beneath its placid appearance lies a complex geological story. The lake sits in a tectonically active region, formed by faulting and uplift, and is surrounded by a network of fractures that have been slowly shifting over millions of years. What has startled scientists this time, however, is the nature of the cracks they have found. These are not ordinary stress fractures in the sediment, but sharp, relatively fresh splits, some extending for hundreds of meters. High-resolution sonar imaging and sub-bottom profiling, tools used to visualize the layers beneath the lakebed, revealed these fissures with unsettling clarity. The cracks appear to have formed recently, suggesting that forces in the Earth's crust beneath Tahoe are changing with unusual speed. Measurements indicate subtle displacements in the lakebed floor, hinting at vertical and horizontal movements that could be linked to deeper tectonic shifts. While the lake's underwater environment is notoriously difficult to study in real time, the clarity of this evidence has left little doubt among the research teams. One of the leading concerns among geologists is that these cracks could be symptomatic of stress building along the fault lines that run beneath and around the Tahoe Basin. The area is no stranger to seismic activity. Faults such as the West Tahoe Fault and the Incline Village Fault have been studied for their potential to produce significant earthquakes. These faults are considered capable of generating quakes in the magnitude 7 range, which in such a geologically confined area could have devastating consequences. If the cracks are indeed linked to renewed fault movement, it could signal a period of heightened seismic risk. Adding to the complexity is the possibility that these cracks might also be related to shifts in subsurface water pressure. Lake Tahoe contains an immense volume of fresh water, and its weight exerts pressure on the crust beneath. Changes in that balance, whether from tectonic uplift, fault slip, or subtle geothermal processes, can influence how sediments and rock layers respond. If water is infiltrating these cracks, it could act as a lubricant along fault planes, potentially making it easier for a slip to occur. The red alert designation is not issued lightly. In geological terms, it's a signal that conditions have been observed which indicate a significant change in underground stability. While this does not necessarily mean an imminent disaster, it does mean the system is under unusual strain and that constant monitoring is essential. Sensors around the lake have been recalibrated to detect even the smallest tremors or shifts in pressure, while satellite-based GPS units are tracking ground deformation across the region. The cracks themselves, in some cases, have irregular shapes, widening and narrowing abruptly, suggesting that they are not purely the result of gradual stress release. In several sections, sediment layers appear displaced, as though something beneath them had bulged upward before splitting apart. This raises questions about possible magmatic or geothermal involvement. While the Tahoe Basin is not known for recent volcanic activity, the Sierra Nevada and its surroundings are geologically linked to areas that have seen volcanic episodes in the past. Even a modest injection of heat or fluids from deeper in the crust could weaken the structural cohesion of the lakebed. For the communities around Lake Tahoe, the presence of these cracks carries a weight that goes beyond scientific curiosity. The lake is central not only to the region's tourism-driven economy, but also to its ecology and water systems. Any disturbance in the stability of its basin could, in extreme cases, alter shorelines, disturb habitats, or release large amounts of sediment into the water, clouding its famously clear depths. Even short of a catastrophic event, shifts in the lakebed could trigger underwater landslides, generating waves that would travel across the lake's surface with dangerous speed. One scenario scientists have been discussing involves the sudden collapse of part of the lakebed slope into deeper water. Lake Tahoe's underwater topography includes steep drop-offs, particularly along its western edge, where ancient landslides have been mapped. A sudden failure in one of these areas, triggered by seismic shaking or by the progressive widening of these cracks, could displace enough water to create a seiche, a standing wave that could oscillate back and forth across the lake. Depending on its amplitude, such a wave could inundate low-lying shore areas within minutes. Historical records and sediment core samples indicate that Lake Tahoe has experienced massive underwater slides in the past, some of which may have been accompanied by waves that surged up to the modern shoreline. The evidence of these ancient events is etched into the layers of sand and silt buried beneath the lake. The new cracks could be the modern harbingers of similar instability. The geological teams working in the area are mapping the fissures with precision, using underwater drones to capture high-definition imagery and to collect sediment samples from along their edges. These samples are being analyzed for signs of recent disturbance, shifts in grain alignment, evidence of shearing, or the presence of displaced organic material that can be carbon dated to establish a timeline. Early findings suggest that at least some of the cracks are less than a decade old, with others possibly forming within the last several years. What complicates matters further is the interconnected nature of Tahoe's geology with the broader Sierra Nevada and Great Basin region. The basin itself is a graben, a depressed block of crust bordered by faults, formed through the slow stretching of the Earth's crust over millions of years. This stretching is still ongoing, and while it usually happens at rates imperceptible to humans, there are times when the stress is released in sudden, dramatic bursts. The detection of these cracks may indicate that such a burst is building beneath the surface. Geologists are also studying whether seasonal factors might be amplifying the stress on the lakebed. Heavy snowfall in the Sierra Nevada, followed by rapid snowmelt, can lead to temporary rises in lake level. Such changes in load can subtly flex the crust, especially in areas already under strain. Over decades, these seasonal cycles can interact with tectonic forces to push a fault system closer to its tipping point. The concern now is that the timing of these cracks coincides with several years of climate-related variability, including swings between drought and heavy precipitation, which could be accelerating the process. Beneath the lake's serene image lies another potential factor: gas seepage. While no large methane reservoirs are known under Lake Tahoe, small quantities of gas trapped in sediment can be released when disturbed. If deeper cracks are providing new pathways for such release, they could weaken overlying sediments, making them more prone to collapse. The bubbles, while perhaps invisible from the surface, would be clear indicators of shifting dynamics below. Monitoring equipment has already been deployed to detect any anomalous gas emissions. The surrounding fault network's history of earthquakes adds gravity to the alert. Seismic records show that the Tahoe Basin has experienced significant quakes in the geologic past, some of which may have been powerful enough to trigger massive underwater landslides and reshape the lake's boundaries. The cracks being observed today might be precursors to similar tectonic adjustments. What is different now is the density of population, infrastructure, and economic activity around the lake. A strong quake today would not be an isolated geological event but a regional crisis. Emergency management agencies have been briefed on the findings, not to induce panic but to ensure readiness. While the red alert is a technical designation primarily for scientists and specialists, it underscores that the system beneath Lake Tahoe is behaving in ways that warrant close, continuous scrutiny. In geological terms, change can happen over thousands of years, or in seconds. The difficulty lies in not knowing which timescale applies to this current episode. Researchers have expressed particular interest in the alignment of the cracks. Some run parallel to known faults, while others cut across them at sharp angles. This irregularity could mean that multiple stress sources are interacting, perhaps combining tectonic movement with deep-seated gravitational sliding of the lake's basin walls. In places, sonar data suggests that sediment layers have shifted sideways as much as 20 centimeters in recent years, a significant amount for underwater geological features. The visual imagery collected by remote vehicles shows sharp-edged fractures, their fresh appearance contrasting with the surrounding sediment that has been smoothed by centuries of water movement. Some of these fractures are partially filled with lighter colored material, possibly silt that is washed in from nearby slopes, suggesting active and ongoing widening. The deeper cracks are darker, disappearing into the murk where even the most advanced lights fail to penetrate, hinting at cavities or conduits leading further down into the crust. Given Lake Tahoe's depth, it reaches over 1,600 feet at its deepest point, any structural change at the bottom represents a massive volume of geological mass in motion. If those changes are part of a cascading chain of events, the potential for sudden and dramatic outcomes is real. Scientists emphasize that the lake, though beautiful, is not static. It is a living, shifting part of the Earth's surface. The cracks are like warning lines on a stressed bridge, signs that forces are at work beyond what is visible to the casual observer. The issuance of the red alert is as much about mobilizing observation and preparedness as it is about forecasting a specific event. Networks of seismometers, GPS stations, and pressure sensors are now transmitting data in real time to research centers. These feeds are being analyzed around the clock for patterns, tiny foreshocks, ground tilting, shifts in water level that might offer clues to the next phase of this story. The aim is to detect any acceleration in activity that might precede a larger movement. For now, the lake continues to sparkle under the mountain sun, its surface unbroken by anything more than a breeze. But beneath that calm lies a growing awareness of the complexity and fragility of the structures holding it in place. The cracks serve as a reminder that even the most seemingly stable landscapes are part of an ever-changing planet, one in which pressure builds in silence, sometimes for centuries, until it finds a way to break through. The questions driving the work at Lake Tahoe now are both scientific and existential. What exactly triggered these fissures at this moment in geological time? Are they an isolated surface phenomenon, or do they connect to deeper systems capable of sudden large-scale movement? How much strain is the Tahoe Basin currently under, and how close is it to releasing that energy? The answers will come slowly in data points and analyses, but each new reading adds urgency to the watch. The cracks themselves, silent and dark, are now the focus of intense scrutiny. Every measurement taken, every sample recovered, every image captured feeds into the broader understanding of what is happening beneath one of America's most cherished natural landmarks. The red alert is more than just a signal of caution. It is an acknowledgement that the forces beneath Lake Tahoe are in motion, and that those forces may have more to reveal in the near future. In the days following the red alert issuance, research vessels have been moving quietly across the lake's expanse, charting routes that intersect with the most active zones of cracking. Crews aboard these ships work in an almost constant cycle of lowering sensors, retrieving data, and redeploying equipment. The urgency is palpable. Every hour matters when dealing with rapidly evolving geological processes, especially in a system as complex as the Tahoe Basin. The fissures are not passive. Some are slowly shifting, widening at rates that, while measured in millimeters, indicate dynamic forces at play. The more detailed the data becomes, the more intricate the picture appears. Sonar imaging has begun to reveal networks of subsidiary fractures branching off from the main cracks, like veins spreading through stone. These smaller fractures suggest that stress is being redistributed across multiple points in the lakebed. In geological systems, such branching patterns can precede a larger rupture, much like hairline fractures in glass before it shatters. The scientists on site are particularly concerned about the speed of this redistribution, as it indicates that the material beneath the lake may be approaching its structural limits. Another layer of complexity emerges when considering the interaction between these cracks and sediment transport within the lake. Lake Tahoe's currents, though subtle, move fine particles across the basin floor. Where the fissures cut across these pathways, sediment can funnel into the openings, temporarily obscuring them from direct observation. But sediment entering a fracture is not just a matter of visibility. It can destabilize slopes by altering the weight distribution along fault-susceptible layers. In certain cases, the sudden infusion of sediment into deep cracks can also block natural pathways for water seepage, redirecting subsurface flows and changing pressure points in unpredictable ways. The hydrostatic pressure in a lake of this depth is immense, and even small changes in how water interacts with underlying rock can have outsized consequences. If the cracks are allowing water to penetrate deeper than before, then over time, freeze-thaw cycles in colder months could act as a wedge, forcing them wider. Even though much of the lake remains unfrozen through the year, the surrounding high-altitude climate means that cold-driven expansion processes can operate in certain submerged layers, especially where trapped gases or pockets of groundwater are involved. Local geology complicates matters further. The Tahoe Basin is framed by the Sierra Nevada Range, composed largely of granitic rock, but its lakebed contains a patchwork of volcanic deposits, glacial sediments, and ancient landslide debris. Each material responds differently to stress. Where the cracks intersect volcanic layers, the fractures tend to be straighter and cleaner, cutting sharply through hardened rock. In contrast, cracks running through glacial sediments appear jagged and uneven, with loose particles sloughing into the voids. This difference in crack morphology could influence how energy from a future seismic event travels through the lakebed. Research teams are now considering whether some of these cracks might be part of an even deeper fault network that extends well beyond the immediate basin. Geological mapping has shown that several regional fault systems align roughly with the observed fissure directions. If the cracks are surface expressions of deeper faults, then their sudden appearance may be a symptom of strain building across a much larger area than previously assumed. This raises the stakes significantly, as it would suggest that the Tahoe Basin is part of a wider stress field primed for release. In such a scenario, the surrounding topography could amplify the effects of a rupture. The steep basin walls and narrow valleys feeding into Lake Tahoe create natural channels for energy waves. An earthquake originating beneath or near the lake would send shock waves ricocheting between these rock boundaries, potentially intensifying ground shaking. For communities perched close to the shoreline or built along steep slopes, this amplification could be particularly dangerous. Beyond seismic implications, the cracks could also be influencing Tahoe's groundwater systems. The lake's hydrology is interconnected with aquifers beneath the surrounding terrain, and shifts in subsurface structures can alter the flow patterns of this hidden network. If the fissures are providing new conduits for water to escape or enter, this could lead to measurable changes in groundwater pressure in nearby wells and springs. Hydrologists are already investigating whether recent shifts in water chemistry or temperature in certain springs might be linked to the new cracks. A particularly intriguing aspect of the findings is the potential role of geothermal influences. While Lake Tahoe is not located in an active volcanic zone, the broader region has pockets of geothermal activity. It is possible that deep-seated heat sources far below the lake are contributing to shifts in rock stability. Even a modest increase in geothermal heat can change the mechanical properties of rock, making it more ductile or prone to deformation. In some cases, it can also cause the slow release of gases, which then seek pathways to the surface, pathways that cracks could readily provide. The drones mapping the lakebed are now equipped with thermal sensors to detect any subtle heat anomalies along the fissure lines. Early results show that in at least 2 locations, the sediment immediately adjacent to cracks is warmer than the surrounding lakebed by several degrees. This might point to fluid movement from deeper, warmer layers, though more investigation is needed before conclusions can be drawn. All of these findings converge on one reality. Lake Tahoe's geological environment is in a state of flux. While the scale of that change remains uncertain, the pace is what alarms scientists most. Geological processes are often slow, unfolding over centuries or millennia. The fact that measurable changes are occurring over just a few years, and in some cases months, means that the forces involved are unusually active. This is precisely why the red alert was issued. The human dimension of this situation is difficult to ignore. The shoreline is lined with homes, resorts, marinas, and infrastructure that support thousands of residents and visitors. Roads and bridges span areas that could be affected by even moderate seismic or landslide activity. Water intakes and treatment facilities depend on the lake's stability to function effectively. A sudden event tied to the fissures could disrupt not just local life, but also regional water supply networks, particularly in parts of Nevada that draw on the Tahoe Basin. Meanwhile, the lake's ecological systems are also at stake. Disturbance of the lakebed could release stored nutrients or sediments that trigger algae blooms, reducing water clarity and altering the ecological balance. Even a single underwater landslide can cloud the water for extended periods. cutting off sunlight to aquatic plants and stressing the species that depend on them. The cracks also present a rare research opportunity. In most tectonic systems, early-stage fault formation occurs deep underground, far from human reach. Here, the lake provides a transparent window into processes that would otherwise be invisible. Scientists can directly observe the initiation and propagation of fractures in near real time, offering valuable insights that could apply to other fault systems worldwide. The urgency of the current situation is thus paired with a sense of scientific fascination, albeit one tempered by the risks involved. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on cracks under Lake Tahoe? What do you think happens next? We want to hear from you. Thank you for watching, and see you next time.